So now we're on page 530 in the notes, and we're going through, this is going to be the last problem in the notes about how to calculate position using in particle motion problems using the fundamental theorem of calculus. And so we've had different techniques and different way that the data has been presented to us in the 3 problems so far, and this is going to be a 4th one. So the table above shows the values of velocity, v of t, in meters per second. So let's keep in mind that those are our units for this problem, of a particle moving along the x-axis at selected values in time. So not only do we not have an equation, we don't even have a graph. We only have the values at a few. So between 0 and 18 seconds, they measured the velocity every 3 seconds. And so that's all the information we have. So all we're going to be able to do is estimate positions using, remember, we can use Riemann sums, which is something we were doing, I don't know, it feels like 2 months ago now. Holy cow, time has flown. All right, so the first question they ask is, what does the value of the integral from 0 to 18 of v of t dt represent? And so if we need to remember, we can go back and look at this. And so looking at part B, it is the net distance the particle travels from 0 to 18 seconds. Okay, these values are all positive, so we might be inclined to think that this is the total distance. I'm not 100% sure, though. We don't really know what this particle is doing in the middle. It might drift to the left and then really speed up and come, make up for that. So describing this as the net distance is the safe way to go here. All right, and now we are going to calculate these using different sums. All right, so this is using a left Riemann sum of 6 subintervals of equal length. We want to estimate the value of the definite integral. Okay, so we've got 1, 2, 3, 4, 5, 6, 7. We've got 7 data values. So the 6 subintervals of equal length are just going to be these right here: 9 to 12, 12 to 15, and 15 to 18. All right, so all of our subintervals are going to have width of 3. Okay, and this is a left Riemann sum. So which values are we going to use to represent the height of the 6 rectangles that we're measuring? Well, what we're going to do is we're going to use 2.3 to represent the first interval, because that's the left bound of that first subinterval. Okay, and so the left Riemann sum, since they're all the same width, I can just throw that width in a great big distributive property. And so 2.3 plus 2.7 plus 2.0 plus 1.3 plus 1.0 plus 1.7. Okay? And so whenever you get Riemann questions, you will be allowed to use your calculator, because there's just too much arithmetic to do there. 2.0 plus 1.3 plus 1.0 plus 1.7. And we're going to multiply that by 3. And so that is 33 for our answer. And what are the units we're going to use? We're adding up a whole bunch of different velocities. And as we said here, a definite integral of velocities is talking about net distance. So net distance, we are going to measure in units of distance, which in this case should be meters. Okay. Problem C, we're going to do the same thing, except this time we're going to use a right Riemann sum. 6 subintervals of equal length. We've got the same definite integral we're trying to measure. So what's going to be the difference between this last problem we did and this next problem where we only need to use the right Riemann sum? Well, we've got 6 subintervals of equal length. It's still going to be a length of 3, except this time we're going to use the right-hand side of each interval. So instead of having everything from the first to the last, but except the last, this time we're going to leave out the first. Plus 2.0, plus 1.3, plus 1.0, plus 1.7, plus 2.1. All right, and so 2.3 plus 2.0 plus 1.3 plus 1.0 plus 1.7 plus 2.1 is equal to 10.4 times 3 is 31.2 meters. All right, so these are two different estimates. Notice we don't really know what this function is doing in the middle, so we don't know which one of these is a better estimate of the actual value. The actual value might be more or less than either of these. We don't even know that it's between these two values. All right, then they want us to use a midpoint Riemann sum with 3 intervals of equal length. So if they want to do that, then our subintervals have got to have length 6. And what are the height of our 3 subintervals going to be? Well, the midpoint of the first one is going to be 2.7. The midpoint of the second interval is going to be 1.3. And the midpoint of the third interval is going to be 1.7. 2.7 plus 1.3 plus 1.7. And then we're going to multiply that by 6. 34.2 meters. Are any of these better than the other? We have no idea. Okay. So using a trapezoidal sum of 6 subintervals of equal length, we want to estimate the value of it again. All right. So this time it's going to be, remember, the area of a trapezoid is 1/2 the width times the sum of the two bases. So that's 2.3 plus 2.7 plus 1/2 times 3 times the sum of these two bases, 2.7 plus 2.0 plus 1/2 times 3 times 2.0 plus 1.3 plus 1/2 times 3 times 1.3 plus 1.0 plus 1/2 times 3 times 1.0 plus 1.7 plus 1/2 times 3 times 1.7 plus 2.1. All right. And if you want to save yourself a little bit of time, once we pull out the things and pull out the common terms, if you're not comfortable with what I'm about to write, you can just write out all 6 trapezoids. There's no shame in doing that. So it's 2.3 plus 2.7 shows up twice. 2.0 shows up twice. 1.3 shows up twice. 1.0 shows up twice. 1.7 shows up twice. And then the last one, 2.1, only shows up once. All right, so 2.3 plus 2.7 plus 2.7 plus 2.0 plus 2. Plus 1.3 plus 1.3 plus 1.0 plus 1.0 plus 1.7 plus 1.7 plus 2.1. And then we want to multiply all that times 3, and then we want to divide that by 2. And so our last estimate is 32.7 meters. Okay. Oof. All right. So these are all different estimates. And we don't have any reason, as I've said before, to trust one of them more than any of the others. It just depends on how well those 6 data points match the entire behavior of the graph. All right. In the last video I make, I will talk about the final problem here because it's a little bit different than the 4 we just did.